In the last video, that was video number 335, we looked at alcohol dehydration reactions and applying Zaitsev's rule to determine the major organic products. Here, in this session, we won't go through the fundamentals of those, but we will talk about how to solve problems where we're asked to predict major organic products of alcohol dehydration reactions. Let's tackle a couple of example problems now. Predicting the major organic product of each reaction below. We'll take each of these examples and work through what the major organic product is based on applying Zaitsev's rule, which we learned about in the previous video. In each of these reactions, the first thing we need to assess is what functional groups we have in the starting materials to allow us to consider what will be present in the product. In any case where we have an acid, such as sulfuric acid, reacting with an alcohol, the predicted reaction was that an alcohol with acid undergoes a so-called dehydration reaction to give an alkene product. Our task is to determine what alkene product we actually need to create here. So to do this, what we examine is that we will remove the OH group from the carbon atom here that has the OH group, and then at one of the adjacent carbon atoms, so that would be the carbon here or the carbon here, we remove a hydrogen atom in order to eliminate H2O from the molecule and put a carbon-carbon double bond in its place. So the carbon-carbon double bond will come here or it will come here in response to removing one of the two hydrogen atoms from this side or the hydrogen atom from this side. Remember that Zaitsev's rule indicates that we want to remove the hydrogen from whatever side will result in giving a product that has more alkyl groups directly bonded to the alkene. So we can imagine if we put the alkene group over here, carbon-carbon double bond right here, and that hydrogen is gone, the alkene group would have two alkyl groups on this carbon, the alkyl group here, that ethyl branch, as well as the carbon coming through the ring. Just because it's in a ring, it still counts. And over here, once our OH group was lost, we have one alkyl group over here coming down this way. So in total, if we put an alkene group here, we'd have three alkyl groups bonded to that alkene. On the other hand, if we put the alkene group over here, our carbon-carbon double bond went right here, we would have alkene group here as one and an alkene group here as the second. That would only be two alkene groups in total. 3 is better than 2, and so we're going to prefer to put the alkene group over here. So I'm going to label this as CC goes here, because that is going to give the product as more alkyl groups directly bonded to the alkene than going over here, which would be the other possible route this could have taken. So I go ahead and draw in my 5-membered ring. We have our ethyl group right here, as it was in the starting material. Nothing has happened there. Put my double bond where it should be, connecting from the ethyl group into the molecule going this way. So I'll go ahead and fill that in, and I'll put it in green to color match what we've done on the left there in our note about where the carbon-carbon bond goes. And then coming in there on the ring, this would be a CH2 group here in the line angle formula. It was a CH2 over here as well, and so on and so forth. And this, to confirm, will be a product that has 3 alkyl branches coming off of it. We can count those out as 1, 2, 3 alkyl branches coming off of the alkene group. We count 3 carbons, in other words, directly bonded to the 2 carbons of the alkene. So we have the alkene carbon here. It's got 1, 2 carbons directly connected to over here. We have 1, so that's 3 alkyl groups in total. If we'd gone the other way, which you could draw that out, and I just erased, I'll back up so it's not erased, you would have instead had just 2 alkyl branches connected there. So that's why we went the route that we did. Now for the next problem, I encourage you to hit pause, try to solve this on your own, see if you get to the right answer, and then we'll go through it together when you hit play. Taking a look at this problem to solve it, we have recognized that our alcohol group is bonded to the carbon atom right here. And so we have 2 positions where we could remove a hydrogen from the adjacent carbon. We could either work from this methyl group here at the far right end of the molecule. That would be a carbon adjacent to this one. Alternatively, if we come over here, what I'll highlight in blue is we could have a carbon atom here as well. So we have to decide whether to remove the hydrogen atom that's bonded here from the blue carbon, or the hydrogen atom that's bonded here from the yellow carbon. The way that we go about that is we decide which way of approaching this would result in a product that had more alkyl groups directly bonded to and fewer hydrogens. If we put the double bond right here, our product that would result from that would have no alkyl groups over on this side, just hydrogens. On this side, we would have just one alkyl group coming this way. On the other hand, if we remove the hydrogen here, what we will find is that putting the double bond right here would give us a product that had 3 alkyl groups directly bonded here, here, and here. And so that's going to be the route that we will go with this, is we will elect to remove the OH group from right here and the hydrogen from right here. And I'll put those in blue boxes there just for further emphasis. So blue box and blue box, that's what we're going to remove. Those are on our adjacent atoms, so therefore the carbon-carbon bond goes here in dissecting what will happen with this. Draw out my 6-membered ring in my final product, keeping my carbons on the same skeleton there because we're not breaking any carbon-carbon bonds completely apart. So we still have 6 atoms in our ring, just redrawing that, and then a 2-carbon chain coming off of it here and here. And then it's at that first carbon of the chain right here where the alcohol group was, and the alkene group's going to go here running toward the ring. So I will put that in as a red double bond there. And counting up the number of alkyl groups directly bonded there, we had 1 coming away from this carbon of the alkene, and then 1 here and 1 here. That makes 3 alkyl groups in total, which was superior to the alternative of taking the carbon-carbon double bond and putting it over on this side rather than putting it here instead. So as you're working through determining the major organic products of dehydration reactions, be mindful that if there's more than one possible product that results from removing an OH from one carbon atom and an H from the adjacent carbon atom, choose the route that would give an alkene that has more alkyl groups, more carbon atoms that are directly bonded to the carbon-carbon double bond.